Hello, I'm Professor Steve Miller. In this lecture, I want to talk about classifications of particular RANS-based turbulence models, and this might be a classical viewpoint. Now, of course, simpler models are going to be cheaper to evaluate computationally, but they don't contain as much physics. So, of course, if you want to have more physically predictive models, then we have to have more complicated and models in less terms. So let's look at just one traditional way of how to classify these models. And the first classification are going to be integral methods. And the second would be Eddy viscosity models. We might abbreviate that as EVM. And there's a number of these. There'll be algebraic. There'll be half equation. There'll be one equation. Two equation. And more recently today, there are multi-equation. These are more exotic and not seen typically in production CFD codes. Then there's a whole class of differential Reynolds stress models. And sometimes we might say that there are algebraic ones, but we're not going to talk too much about that. And then opposing to these types of Reynolds-Averaged Navier-Stokes closures, we'll just say for now that there's a whole nother class of type of models, and we'll just lump it all into large Eddy simulation. And of course, maybe just direct methods, numerical methods where there's no modeling, we just directly solve the Navier-Stokes equations. Those might be called direct numerical simulation. And generally, in orders of complexity, the integral methods are, the least complex and run very fast, even on like a small calculator, pocket phone. And then they become more complex as you go down the list. This class of the Reynolds stress models are more complex than RANS closure. LES can take supercomputers to run usually, and direct numerical simulations certainly should run on a very large supercomputer. So let's just talk about each of these a tiny bit to give you an overview, and then in future lectures we'll try and show some of the mathematical details. So of course the first one is the integral methods. So these are generally the most simple methods, and they do not explicitly cover the variations in turbulence across like a boundary layer thickness, if it's a boundary layer equations. And they'll usually make use of integral quantities, which is where of course they come with their name, and they'll be represented by shape factors. And for those of you who've been through a traditional aerospace engineering course will recognize the idea of shape factors, and they've even made their way into traditional boundary layer theory. But the shape factor, like in a boundary layer theory code, will usually be like a function of streamwise position, x, if x is the streamwise position. So in these ways, like our traditional partial differential equations, which we derived earlier, like the RANS equations for particular flows and particular turbulence statistics, are replaced by ODEs. So this takes the partial differential equations, PDE, and replaces them as ODE systems. And that's why it's so powerful, because of course certain ODEs might have analytical solutions, and certainly ordinary differential equations are simpler to solve numerically. Now, if particular initial conditions are known at, say, x naught, and if we look at a boundary layer flow and we go downstream, and we know things like the initial shape factor, we'll just call it capital theta, then all other quantities can be known downstream and increasing x, which is just wonderful. And so a simple ODE numerical integrator can advance our solution of some given parameters and move downstream. Now, the unfortunate part of these integral methods, even though they're fast, is that they are not very precise in modeling the actual turbulence. In fact, these methods might heavily rely on empirical relations of the integral parameters. They're extremely simple and fast, but that means they don't have much predictive capability out of their realm of applicable design spaces. So this means, like for example, we might be able to define and create a complete airfoil or simple fuselage in like a systems design code, but you can't expect to recover exact turbulence statistics and make it like a predictive model of flow. And that's really the first type of models that try to account for the turbulence in like a numerical method that was fast for aeronautical design. Now there's a number of more useful methods where they still try and solve the PDEs, but they need to model the Reynolds stress. And I'll just write Reynolds as RE, stress. As you remember, that's UI, UJ, prime, prime, bar. And that first classifications of models will be, of course, Eddy viscosity models. Right there. And the Eddy viscosity models will relate the Reynolds stress, actually all of them, to the time averaged velocity gradient through the introduction of the so-called Eddy viscosity. So just like we have a traditional viscosity of fluids, there'll be a new effective Eddy viscosity, which is like an additional viscosity due to the motion of the turbulence. You might also think this as a turbulent viscosity. So we'll write just the kinematic viscosity as new, and we'll write turbulent viscosity, or the Eddy viscosity, as nu sub T. So this is just the traditional viscosity, and then this is the turbulent viscosity. So that's what you're seeing when you see these types of models in your computational fluid dynamics code. And so let's make the most simple Boozanesque type Eddy viscosity model. And we'll write the Reynolds stresses, negative UI, UJ, prime, prime, bar, is equal to the Eddy viscosity. There's our model. So this is a model. We're just writing it down. Partial UI, partial xj, plus partial uj, partial xi, minus 2/3 of the turbulent kinetic energy of delta ij. Now, so this is equation, we'll call this equation 21 in our class series. And you see in this particular equation, on the left-hand side, we have the negative of the Reynolds stress. The right-hand side is the Eddy viscosity, which is unknown. It can vary in space and time, only in space if it's a steady model. We have our velocity gradients. We have 2/3. K, remember, is the turbulent kinetic energy. And we derived the transport equation for that previously. And delta ij, we talked about previously. This is the Kronecker delta function. And if you remember, if I equals j, it is 1, and if I is not equal to j, it is 0. And typically, of course, these subscripts I and j vary from 1 to 3 integers. Now you'll notice the last term in this particular equation right here. Let's look at that, and you'll see that if it's negative 2/3 of k delta ij, it will be introduced, and it's at this location, to make the whole equation consistent when the trace of the Reynolds stress is taken. So remember, the trace of the Reynolds stress goes as, of course, the turbulent kinetic energy. And do the continuity equation when J is equal to I in the first term on the left-hand side right here, we'll see that, of course, it goes to 0 because partial ui partial xi from 1 to 3 is 0 if it's an incompressible flow. So by setting J equals I, we can now find the particularly correct and recover the correct expression of negative ui prime prime bar equals negative 2k in, of course, 3 dimensions. So that works perfectly, and we're quite happy. So that's part of where this equation comes from. We're setting it so that we can enable K being equal to the trace of the Reynolds stress, and we've introduced this eddy viscosity term for the off-diagonal terms so that there's some sort of like extra viscosity due to turbulence. So that's the model. And of course, we have to come up and try and find how now this new variable, nu sub t, varies within the flow. What if we make a boundary layer assumption? For the general eddy viscosity model, what happens? Well, we make the same type of assumptions like we did earlier, and I forgot to label this equation. I want to label this equation 22. Right there in blue. Sorry about that. That way I can go to 23 in my notes. And we'll make this assumption just like we did in the previous class, which the flow is 2D, and of course the velocity is u component velocity is much larger than v, and only gradients in the y direction really matter, and they're very small in the x direction, and it's steady in 2D. Okay, so if we do that and look at equations 21 and 22, what do we get? Well, we'll get negative u prime v prime bar equals nu t of partial u partial y. So this is our new eddy viscosity model relating, of course, Reynolds stress with eddy viscosity. It's only the gradient of u, which is the velocity component in the x direction, and y is the cross-stream direction. What happens to the other components of the Reynolds stress? Well, u prime squared bar will be equal to v prime squared bar by definition. It's equal to w prime squared bar, which is equal to 2/3 of the turbulent kinetic energy. That's wonderful. So within this eddy viscosity concept, we can indeed assume that there's an analogy between the turbulent transport and molecular transport. And we'll emphasize that this particular analogy is in contrast to the typical molecular viscosity nu. So this whole thing is not like an analogy with nu. That's not equal to nu. So remember, the turbulent viscosity is not a particular property of the fluid like viscosity or C sub P or C sub V or the gas constant R or something. And nu sub T varies strongly throughout the flow, in space, and if it's an unsteady flow, time. So it's a whole new function we need to define. So if we don't make any other specification of the eddy viscosity, then of course there can be no modeling for the Reynolds stresses that have to be made, except for the case that it's a scalar, not a tensor. So we can assume that nu t is scalar, and of course it's positive and real. This means that we still have to model this term in some way, and the general way to write it for these types of models will be equation 24, and we'll write the eddy viscosity nu sub t goes as some function of x and y of some velocity scale, which we'll write as capital V, and some length scale. So capital V and L is a velocity scale, and L is a length scale. And there's really only one. These don't vary like in a turbulent cascade if you studied turbulence theory. So we also assumed in this relation that it's steady, right? Because if it was unsteady, then F would be X, Y, Z, and T, for example, in three-dimensional unsteady flow, right here, right? So the question becomes, what should V and L be? And it so happens that we can kind of talk about the different models and their classifications through this way. Oh, and I should also mention, of course, for this to be dimensionally correct, we would want F to be dimensionless. So what would V, L, and F be? Well, in the first classification of models, there are indeed algebraic models. And in algebraic models, there'll be, of course, algebraic expressions for L and V. These will be algebraic. That's why they're called algebraic models. Perhaps the most well-known algebraic model is Prandtl's mixing length model. Named after Ludwig Prandtl, one of the greatest fluid dynamicists who ever lived. And that would just set F equals to 1, L equals some length scale, we'll call it L sub m, and V equals L sub m of partial U partial Y. And this is an excellent model for a simple attached incompressible boundary layer flow. Now, we still haven't said what L sub m might be. Well, perhaps we can say L sub m will go as, and this is a model, of some constant, we'll call it kappa, times y. So for a boundary layer, there's the distance from the wall y, and there's the streamwise direction x. So you can see our velocity goes as the length times the magnitude of the derivative of the velocity in the streamwise direction with respect to the wall normal direction. L is a length scale, which we just say goes as a constant times the distance to the wall, and F is 1. And so that way, F is 1, but we're still letting our length scale and velocity grow. The length scale will grow in a linear way, and the velocity grows in a nonlinear way. So there's other well-known models. Two of the most famous ones after Prandtl's are the Baldwin and Lomax model. And of course, the Sebecki-Smith model. And we will outline these models in later sections. The next model that's interesting is the so-called half algebraic models. We'll call these half algebraic models. And perhaps the most famous one is of Johnson and King. And we'll talk about this later. But this is referred to a half equation model because, of course, in addition to the algebraic relations, it also solves an ordinary differential equation for one particular quantity which is related to the turbulent velocity scale, capital V. Okay, so there's like replacing this capital V term up here in Prandtl's model with a differential equation relation, and retaining the algebraic relations on the other part of the model. So this is called like a half model or half algebraic model because only part of it is solved through a differential equation. Those are really not used much today, except for large-scale calculations, and you won't see them too much. And a lot of people today in their professional CFD codes use RANS closures involving one or two equations. Let's look at the one equation model. And we'll show all the details of these models later on. I'm just giving you an overview and classification. So one equation model, besides, of course, the algebraic expressions, will solve one partial differential equation for the turbulence. Partial differential equation for turbulence. So there's lots of famous examples. Today, probably the most famous one is the Spallart Olmos model. And that's in almost every industrial and government CFD code in the world. Perhaps another extremely well-known but less used one-equation model is the so-called KL model of Bradshaw and his collaborators. And we'll show this model later on. But it solves one PDE for turbulent kinetic energy, K, which we showed earlier. And it solves an algebraic equation for the length scale, L. Now, the Speller-Almalis model actually solves a single equation for a parameter S, which isn't really particular K or L. Anyway, that's enough about the one-equation models. We'll look at particular forms soon. Let's look now and talk about two-equation models, which are more expensive. And as you guessed, a two-equation model solves two PDEs, partial differential equations, for closure and for the turbulence. So we're closing the RANS equations with two additional partial differential equations and sometimes additional algebraic equations and simple constants. So these are an interesting class of models, and they're very well known. And there's two types which are mostly known. One is the K epsilon model. And the K epsilon model solves one equation, one PDE for K, and of course one PDE for epsilon. Turbulent kinetic energy is K, and epsilon is, of course, dissipation of turbulent kinetic energy. So if we look for K and E and look for the dimensions with respect to equation, say, 24, which we wrote up here, we will say, and you can think about it for a second, but you'll see that V equals K to the 1/2, right? Because K has meters squared per second squared units. And L will be K to the 3/2 over epsilon, which of course gives you the units of meters, right? And this is meters per second. And you can easily discover what this is. This is meters squared per second squared, 3/2 power, all over meters per second squared. And that gives us meters, so the dimensions should check out. It's that simple if you put it in that way. If we substitute these two relations into equation 24, we can get a new simple relation for the Eddy viscosity, which can be used to close the model, of course. Mu T equals C sum mu of K squared over epsilon. Here, C sum mu is usually a constant, which is calibrated against a particular experiment or well-known analytical result, if it's possible to know one. You might say, well, C mu might also be interpreted as a function of x and t. If it's steady, of course, t goes away. Typical values of C mu in practice we find to be 0.09. So if you're using a professional CFD code and you bring up a K epsilon solver and you would find the Eddy viscosity from K squared and epsilon, you'll see that C mu is there 0.09. You might also see that in the literature of the particular models. I've already mentioned that there's the K epsilon model and also the K omega model. The K omega model was originally proposed by the academician Andrei Kolmogorov in the Soviet Union. The K epsilon model was proposed by, I believe, von Karman and Prandtl at different times. It can be argued about who proposed it first. But certainly the K omega model might be seen as a little more physical, in my opinion. But nonetheless, we'll get into that later and show examples. So the K omega type models is also two equation, of course, meaning it solves one equation for K, just like the K epsilon model, and also one equation for omega, which is specific dissipation. So omega is specific dissipation of turbulent kinetic energy, and we'll define that in a second. And so how is this related to equation 24? Oh, and I wanted to label this equation 26, excuse me. Okay. Well, I will say that omega must be proportional to epsilon over k based on dimensional analysis. And then we'll say v is once again k to the 1/2 power, just like the model of k epsilon. And therefore, for dimensionality to be correct, we'll say L is, of course, k to the 1/2 over omega. And omega should have, omega should have the dimensions of 1/2, if I'm correct. This is in meters, this is in meters per second, and I think all the dimensions check out. Then you can try it for yourself. So what does this mean? This means that just like k epsilon can give us an eddy viscosity, k omega can too. And we'll find that mu t, for this is k omega, mind you, should be equal to alpha times k over omega. A little bit simpler than our previous equation of c mu of k squared over epsilon. I'm using alpha here and c mu over there because it's just traditional. So in this case, f is replaced by alpha. So there's also other two equation models, and they might also be for, say, k-L or k-tau. This is a turbulent kinetic energy length scale model or turbulent kinetic energy time scale model, where L and tau are just going to be single time or length scales. So you can see, instead of like relating the length scales and velocity scales explicitly, you can actually create differential equations for them. These types of models are less popular. Let's make some notes about these types of models. So first we'll note that all these two types of equation models can absolutely be transformed into each other. And there's just certain advantages or disadvantages for using different forms, and people in the turbulence community discuss them at length. For example, the k epsilon model might be transformed into a k omega model through the relation of epsilon equals k omega. In fact, if you find a solution of a k omega model, you can easily try and seek the dissipation by multiplication through k. Sometimes there's some constants in here depending on the model formulation. So you have to be really careful about what your model constants are for your flows to be able to convert from one type to the other, or even derive other types of data. There's particular restrictions on these models. Let's just list a few out here. So first of all, you can see all these eddy viscosity two equation models depend on a linear relation between the Reynolds stress and the gradient of the velocity field. So of course we can relax that assumption and make it nonlinear, and there can be discussions about that, and no doubt particular types of fluids or theoretical fluids that break these rules. And we also assumed a scalar characteristic of the eddy viscosity, and that may not be true. It is an assumption, a good one for many types of flows. We assumed there's is only one velocity and length scale in the models. And there's certainly types of models which use types of spectra or multiple length scales or velocities, but these are kind of exotic and you won't see them too much in like a production computational fluid dynamics code. Finally, the so-called anisotropy is not explicitly accounted for. And then you saw in our boundary layer calculation, we had u prime squared equals v prime squared equals w prime squared equals 2/3 k. And so that type of turbulence model doesn't contain anisotropy of the turbulence. And we're not even really calculating these quantities. We're only calculating k. So we have no idea about what the anisotropy is in a boundary layer type flow predicted by this model. But we know from measurement the boundary layers are certainly anisotropic, especially, of course, within the boundary layer turbulence. So if flows are more complex than, say, just simple shear layers that are steady and incompressible, then these types of forms are going to break down. And just some examples of flows where these assumptions are breaking down, we'll give them here. For example, flows with abrupt changes in U, which is a lot of types of flows. Say sharp or strongly curved surfaces. That's another great example. Sometimes near stagnation regions, right, where flow stagnates. Highly three-dimensional flows. And maybe flows with high unsteadiness, like shedding and separation. Separation or unsteadiness. Uh-oh, that's a lot of type of flows I can think of. Especially when boundary layer flows separate, these models themselves aren't really conducive. That is, there's even a lot of research today in development of models that accurately predict transition of flow from laminar to turbulent and also predict where separation occurs. And these types of models are usually using our third major class, which we'll talk a little bit about, and these are called the so-called differential Reynolds stress models. And this is where we're not necessarily solving for a transport equation for K. We can still do that, but we're forming differential equations for each component of the Reynolds stress tensor, which, as you know, is Ui prime Uj prime bar. And this is a, of course, 3x3 tensor, and it has the property, usually for most fluids we're interested in aerospace, of being symmetric. So if it has, of course, 9 components and it's symmetric, 9 components and symmetric, there's really only a need for 6 differential equations to model each of the components, because of course it has a symmetric property. Of course, these models also usually have to solve an equation of, say, dissipation. So just like our 2 equation models have to solve for K and maybe epsilon, these models have to solve 6 differential equations for the trace and off-diagonal terms of the Reynolds stress, and of course another equation which corresponds to, say, dissipation. One of the good things about this approach is that we don't necessarily have to worry about the production of turbulent kinetic energy through P, as you remember through previous lectures, which is production. And therefore, we don't have to worry about some of these issues which we listed up here, which are drawbacks of the typical K epsilon, K omega models. Now that's the big overview of the RANS closure models that I'm going to overview, and I might do a few extra over time. Maybe I'll look at some more contemporary models from their articles. But you should also know that there's other avenues of turbulence modeling, and we're looking at RANS-based closures in this series of lectures. I already mentioned large eddy simulation, which I'll just call now LES. And LES is just what it means. You're only using the computer to resolve through a filtered set of Navier-Stokes equations the largest scales of turbulence. So we might draw these as large scales of turbulence in a chaotic field. And this might have a length scale as L. And we're resolving scales like integral scales and smaller scales. But if there's tiny little scales of turbulence like this, which I'm drawing right here, we're not resolving those with the numerical simulation. We're modeling them. So in the big picture, LES resolves numerically the largest scales and models with turbulence theory and empirical closure the smallest scales. And the advantageous part of this is that most of the energy in the flow, E, the dominant energy, is mostly contained in the largest scales, which is good, right? So that's a happy thing. And that's all I want to say about LES. I've given a lecture or two on LES in my CFD class, which is on YouTube and many other places, and we've done LES and research over the years. And of course, there's mixtures of LES and RANS called detached eddy simulation, and these are specialized things that you can look more into. I also wanted to mention quickly something some people like to get into mostly for research is direct numerical simulation. DNS. And this is where we just simply use classical or maybe advanced numerical methods to directly numerically evaluate approximate solutions as numerically accurate solutions of the Navier-Stokes equation. So this is just numerical evaluation of the Navier-Stokes equations. And maybe a gas law and energy equation if it's compressible. If incompressible, just do Navier-Stokes. And it's usually done for research, and since you're not doing any modeling, you're not doing any RANS, you're not doing any LES or any other exotic technique, these are the most expensive approaches. But the nice thing is you get a time-dependent, a three-dimensional time-dependent solution, but you're going to have to use a supercomputer to resolve high Reynolds numbers. And it remains an area of research which will likely be around for the rest of my life. So today we just talked about some of these classifications of models. We talked about, of course, zero equation or so-called algebraic models, use that interchangeably, half equation, one equation, two equation, the differential Reynolds stress. There's also something called algebraic Reynolds stress. And we talked a little bit about large eddy simulation, which isn't the focus of these talks, and of course DNS, which isn't the focus of these talks. But just be aware that they're there. And one avenue many people go down today is LES instead of RANS. And in these coming lectures, I'm going to try and highlight some of the most famous models in the classical RANS categories and just show you their terms and some of the physical thought behind their formulation. Thanks a lot for your time today. I'm Professor Steve Miller.